Ladies and gentlemen, boys and girls, welcome to another episode of Transparent Physics. In this lesson, we are going to continue our series on energy, work, and power. Specifically, we're going to look at a sample solution involving net work. And just real quick, as we're working through the solution, if at any point you're like, that makes sense, feel free to like the video. If you have any questions or comments about the way in which I go about solving it, leave them in the field below. And to learn more about what's coming next from Transparent Physics and to help the channel grow, always appreciate the subscriptions. All right, so let's take a look at this problem using our QUIPS format. That means read the question, underline the important information, get the initial information, figure out your procedure, your process, and then get your solution. And for this problem, we have a special bonus challenge because in the real world, this is not the first time I'm working out this problem. I got about a quarter of the way through it, and I realized I did not include an important piece of initial information in the problem. So we're going to turn this into a little bit of a game. I'm going to start working through this solution, and I want you trying to figure out what piece of information I should have given you, but I didn't. And don't worry, I'll tell you before we get too far into it, but see if you can figure it out on your own. So let's take a look here. First thing we do is read the question and underline. So we have a 20 kilogram box that is pushed up a ramp that makes an angle of 25 degrees with respect to the horizontal. The 125 Newton push is directed parallel to a frictionless ramp, and we want to solve for the net work. So going through the important information, we see the box is 20 kilograms. That might be important. It's pushed up a ramp that makes an angle of 25 degrees with respect to the horizontal. So I bet 25 degrees with respect to the horizontal will be important. It tells us the magnitude of the push. We also know that the orientation is parallel to the ramp. They also sneak in the fact that it's frictionless, so that's cool. That gives us one less thing to worry about. And we're interested in solving for the net work. So we've established the information that they've given us so far. Next up is a sketch. Okay, so we have a ramp that makes an angle of 25 degrees with respect to the horizontal. We have a box on the ramp, and that box is pushed up a certain distance. So we have our displacement. And we have one force that they absolutely give us to start with, and that is the push. Let's see if we can color coordinate this a little bit. Yeah, do that. All right. So we have a push going up the ramp, and they give us the magnitude of the push as 125 newtons. Now, they only specifically mention one push, but there are other pushes and pulls going on at the same time. We just sort of have to infer them from the problem. It does give us a mass of a box. I guess it wouldn't really be that significant of a problem if the box didn't weigh anything. So there is going to be a weight acting down. We won't worry about the magnitude of that yet. So we have a push going along the ramp, a weight acting down, and also not specified, but part of reality, the box is not falling down through the ramp, so the ramp is pushing up on the box. And some of longtime viewers might recognize that we call that force the normal force. The normal force is the force that keeps objects from passing through surfaces they press against. So we have three forces now. We have a push, which we know the magnitude of. We have a weight, which we don't know the magnitude of, but we can figure it out. Normal force will be a little bit harder to figure out, but stick with me and we'll go from there. Okay, and as a reminder then, this all gets tied together using the equation work equals F d cosine theta. And at this point, I will reveal the piece of information that I didn't give you that you were going to need. And so if we're solving for the net work, so this is our unknown here. We do not have information provided about the displacement. we're going to need that in order to solve for the work. So when I wrote up this problem initially, I mean, my solution, I have the displacement. I just forgot to type it into the problem when I was putting it into the computer. So the problem should officially state that the displacement is 5 meters. The box gets pushed up the ramp 5 meters. So if you figured out the displacement was missing, good for you. Add 1 point to your score for this exercise. Okay, so next up we need to solve for the individual works to get the net work. The net work, by definition, just like net force is the sum of all the forces. Net work is the sum of all the works. So we're looking for the work done by the push, the work done by the normal force, and the work done by the weight. And I'm just going to spell out weight so we don't have a double W there. So we need to figure out each of those individual works, add them together, bada boo, bada bing, and we get the net weight. Next step in the process is to figure out the angle relationship between the force and displacement vectors for each of the 3 scenarios, for each of the 3 forces. So to start with, we have the push, and those relationships, we have our displacement going up, and in this case the push is directed right along the surface with the displacement. So whenever the 2 arrows are pointing in the same direction, the angle between them is going to be 0 degrees. So the angle for the push is 0 degrees. Remember, we're not taking it with respect to the positive x-axis anymore. Many of you, in solving these out throughout the years would be used to saying, well, that angle would be 25 degrees. Yes, the angle is 25 degrees with respect to the horizontal, but when we're solving for net work, we're only concerned about the angle between the force and displacement vectors, not the actual angle they're pointing at. And that is a bit of adjustment for a lot of people. All right, next up we'll do the normal force. What color was that? I think it's this color. Okay. So the normal force, the displacement is still going up the ramp. And in this case, the normal force is actually going to look like this. We know that because the normal force is called the normal force because it makes an angle that's perpendicular with respect to the surface. So normal force is always going to be at 90 degrees with respect to the surface. And that can be written like this then, 90 degrees. And that's a bit of a saving grace. We'll talk about why that's the case in a moment here. And then finally, we have the weight. And again, we have our displacement going up like this. The weight acts straight down. So what does that mean in terms of the angle? Well, we can take a look at this and say, hey, there is a surface. We know that the weight acts straight down with respect to the horizontal, so we know that this angle in here is 90 degrees. And we're given the fact that this angle up here is 25 degrees. So we can add those together. So the angle for the weight is going to be 90 plus 125, 90 plus 25, which is equal to 115 degrees. Okay, and that's the magnitude of the angle between the displacement and the weight vector. And there we go, we have our 3 angles. Again, I strongly encourage anytime you have a work problem like this, that you do a quick sketch of the forces and the displacements just to make sure you're getting the angles right. If you screw up the angles, everything else goes south from there. All right, and then we just need to plug all those things in with our displacement of 5 meters and see what we get. So we'll just work our way down the list. So the work done by the push is equal to the force of the push times the displacement times the cosine of the angle between those 2 values. So we were given that it's 125 newtons over 5 meters. And that's the cosine of 0 degrees. The cosine of 0 degrees is 1. Whenever the angle is 0, you get your maximum amount of work done because the force is acting directly in the direction of the displacement. So 125 times 5 gets us 625 newtons times meters, and a newton meter is a joule. And that's going to be a positive value. Cosine of 0 is positive 1. All right, next up is the normal force. Work done by the normal force. Now this looks like it could be a bit of a pickle right here, because there's something we don't know. We don't actually know the magnitude of the normal force right now. And that would actually be, that would be a couple steps to actually figure out. So that would actually very much slow us down. We don't know what this value is. We know that this is 5 meters. And we know that this is the cosine of 90 degrees. So our saving grace here is to recognize the fact that it really doesn't matter what the normal force is, because what's the cosine of 90? Cosine of 90 is 0. So this whole term goes away. Anything multiplied by 0 is 0. So there is no work done by the normal force, because the normal force is directed perpendicular to the displacement. So doesn't matter how much work, it doesn't matter how much force the normal force has. It doesn't factor into our solution. So that's a little bit of a relief that we don't actually have to solve out for the normal force there. And then finally, the work done by the weight. So we have the force from the weight, the displacement, and the cosine between the weight and displacement vector. And at this point, some people might plug in the force of weight to be 20 kilograms. That would not be correct. Weight is equal to mg. So we take 20 kilograms times 9.80 meters per second squared, and we get 196 newtons. Resist the temptation to put a negative sign there. Yes, weight is acting down. We're not worried about that for this scenario. We just need to know the magnitude of the weight. How much weight is there? So we know that the weight now is 196 newtons. The displacement is still 5 meters. And the cosine of the angle between the weight and displacement vectors is 115 degrees. And this guy right here is where the negative sign pops out. The angle is greater than 90 degrees, so we end up getting a negative value. So when you take the cosine of 115 times 5 times 196, you plug all those in your calculator, you actually end up with a negative value. Negative 414 joules. Okay? Which means that the work done by the push is adding energy to the object. The work done by the weight is taking energy away from the object. The weight is acting against the displacement. So when we put it all together and we add the three of those terms together, the net work is simply going to be positive 625 joules. Plus 0. I'll put it in there for completeness sake. And minus 414. And then we're done. You put it in your calculator, add them all together. You get a net work of positive 211 joules done in this circumstance. And there we go. Okay, then a couple closing thoughts. As always, whenever I talk about work, it is important that you carefully sketch the displacement and force vectors, because this shows you the angle. And when you know the angle, you use that to help you figure out the cosine of theta, and that tells you whether you're dealing with positive or negative work. An extremely important consideration in solving for work. That extra sketch, I know Students don't like to do that, but it is very helpful in these circumstances to make sure you're getting the answer you should be getting. And as always, thanks for watching. Hopefully the process of solving for net work from a variety of forces acting on an object is a little clearer for you now, thanks to this lesson from Transparent Physics.